of Organic Chemistry second year. Basically, in this course, we are going to talk about two spectroscopies, that is UV visible spectroscopy and also the IR spectroscopy. Since it is your first encounter with spectroscopy, so we will spend one session on introduction to spectroscopy, that is this session was dedicated to some kind of general introduction to spectroscopy. And then thereafter, we will build on this and talk about UV spectroscopy, different aspects of that. What is the original spectrum, how does the spectrum look like, what are the factors that affect them, and what kind of information can we get from these spectra. So, that will be the basic domain of this particular course here. Okay. Now, today's session is planned as follows, that is, to begin with, we will define what is spectroscopy, and then thereafter we will touch upon what is EM radiation and what are their characteristics there. Thereafter, we will try to recall the quantum mechanical nature of molecules. Having done that, we will try to learn about how does the radiation and matter interact, what are the ways of these kind of interactions possible there, and then thereafter we will see what is a spectrum and what are its characteristics there, and then towards the end we will try to sum up what we do in today's session. Okay. Now, what is spectroscopy? Spectroscopy basically is the study of interaction of electromagnetic radiation with matter, and it is used for variety of things. The most important for an organic chemist is the structural elucidation of molecules. Another kind of an application of spectroscopy is in terms of quantification of different kind of analytes. That will be very pertinent when you talk about UV visible spectroscopy. The third kind of a domain of spectroscopy is the interaction studies, wherein we can think of different kind of molecules. If they are interacting, we can use spectroscopy to study such kind of an interaction. And then nowadays we use it extensively for diagnostics as well. Diagnostic again comes from both of these are contributing to the diagnostics and all. So, it is a very versatile and useful tool in the hands of organic chemist or chemist in general. Okay. Now, since it is the study of interaction of radiation and matter, we need to know what is radiation and what is matter. So, we will start with learning about, trying to recall for ourselves what do we understand by EM radiation. You will recall that electromagnetic radiation or EM radiation as it is called is basically a form of energy which is transmitted through space at very large velocities, 3 into 10⁸ meters per second in vacuum. That is a fixed kind of a constant velocity of light as it is. Now, this also passes very readily through the vacuum because we do not need a medium for the transmission of EM radiation. There are two important characteristics of that. And as regards how do we look at, how do we visualize EM radiation? EM radiation can be seen basically as oscillatory electrical and magnetic fields. Let us see how does it look like. That is basically what I am referring to. That is, suppose we have a EM radiation which is proceeding or propagating in this particular direction shown by this arrow over here. So, this radiation can be perceived to be made up of two oscillatory fields there. One oscillatory field shown in blue over here is this. That means, there is an oscillation in the y dimension or z dimension as the case may be, because suppose I take this as an x dimension, this is in z dimension. And on the y dimension, the dimension perpendicular to this blue thing, we have an oscillatory field over there. So, this is my oscillatory electrical field, this represents my oscillatory magnetic field. So, what we have is, we have got oscillatory electrical and magnetic fields which are oscillating perpendicular to each other and also perpendicular to the direction of propagation. So, there are three things there. We look at this here, this is my direction of propagation of radiation, this is my electrical field there. So, this means this is oscillating like this, and this is my magnetic field there which oscillates like this. So, the three are mutually perpendicular to each other, direction of propagation, electrical field, magnetic field there. So, that is my EM radiation. Now, this EM radiation has got certain characteristics. Let us look at, because they are very important, we will be coming across this very often in the context of spectroscopy. And the characteristics happen to be, the first one is amplitude. Amplitude basically refers to the height of the crests or depth of the troughs of a wave. Let us understand this. Now, suppose let us look at this blue wave here. So, this is the wave which is propagating like this. Now, if you have this kind of a wave and a kind of oscillatory disturbance over there, we find that the maximas here are called as the crests and the minimas of a wave are referred to as troughs. Okay. So, when we talk about amplitude, amplitude basically refers to, as I said, the height of the crests. That means, if this is my reference point here, from here what is the height here? So, this is the amplitude of, say this is my amplitude of the blue wave here, this is the amplitude of the red wave there. So, amplitude basically refers to the height of crest or depth of the troughs there. This amplitude basically is a measure of the radiant power and the intensity of the radiation there. And in this picture what we see is that the blue wave has got higher amplitude. As you can see in terms of the height of the crest over there, for the blue wave is more than the red wave here. But important point which I want to bring home is that it is a measure of the power of the wave there. Let us look at these pictures there. Look at this is a scene of a seashore here. We see that there are small waves are coming over there. Now, suppose someone is standing on the seashore here and these waves come, they will come and hit the person, and then it will just cause very pleasant experience for the person. On the other hand, if I have another kind of a wave coming there, a very high amplitude wave is coming there, if this comes and tries to strike the person on the shore, it definitely is going to knock the person off, because that is the meaning of it. That means a wave with high amplitude has got more power behind it. That is what I want to bring home here. That is, the amplitude basically is a measure of the radiant power there. Okay. The second important characteristic of EM radiation is the wavelength. Wavelength basically is defined as is a linear distance between two consecutive wave crests or wave troughs, or the distance of the complete cycle. Let us look at it. Now, I am showing you two waves over here. Let us look at any one of them, say the blue one. So, if I see it here, say this wave starts here, that is how it is moving, propagating here. So, if I look at the distance between the two crests here, or maybe for the red wave here I have shown the two troughs here. So, for this happens to be the wavelength of the red wave here, this happens to be the wavelength of the blue wave there. Or other way of visualizing it, suppose I am looking at the blue wave here, I suppose I start from somewhere here, I go down like this, I come back here, I go up there and come back to same position here. So, this is one complete cycle. So, each one of them represents the wavelength, length of one wave. Let us look at another picture here, this probably makes it more clear. So, I am showing you an EM radiation, both the components of that, the electrical vector as well as the magnetic component there. What you see is the wavelength basically refers to the distance between the two crests here or the two troughs, or in this case I am showing you one full wave over here. So, that is the meaning of wavelength. This wavelength basically is represented in terms of a Greek letter called as lambda. That is how we represent a wavelength, and the units, it has got dimensions, as it is called as wavelength, it has got dimensions of length and has got units. SI unit happen to be meter, but typically meter is very long. So, normally when we express these things, we talk in terms of centimeter, micrometer, nanometer, or even angstrom units. So, they are the commonly used units over there, and it is important to know about the conversions between some of the three important ones I am sharing with you. One angstrom happens to be 1 into 10 to the minus 10 meters, it is a very small unit here. A nanometer very commonly used is 1 into 10 to the minus 9 meter, and a micrometer is 10 to the minus 6 meters there. So, wavelength basically is length of the wave, that is important. Another parameter happens to be the frequency. Frequency basically is the number of wavelengths or the wave crests, you can say, that pass through a given point per second. Now, suppose a wave is coming towards you or going away from you, and if I look at one point of reference, how many wavelengths pass through that point in a given time, that is a frequency. So many wavelengths per unit time. Let us look at this picture here. Now, suppose I am again showing you two waves here, one the red one is the blue one here, and suppose I am looking at this point of reference for me, and if the two waves are propagating at the same speed, that means they will travel their distance from A to B in the same amount of time, and if they travel this distance, and if I look at from this point of view here, I will find that the red wave passes through this point B more often than the blue one here. That means, this red wave has got higher frequency as compared to the blue wave there. So, we can imagine frequency to be the number of wavelengths which will pass through point of reference per unit time is important here. Since per unit time is important here, so this is given a symbol as nu, that is a typical symbol for this, and as I was just mentioning that since per second is important, per unit time is important, the unit happens to be second inverse or per second. Second inverse is used more often, and it has been given a name as hertz. Hz is a symbol for that. And the frequency and the wavelength are related as follows, that is, the frequency is equal to c, that is the velocity of light, velocity of radiation, by lambda, that is the wavelength there. That is a very common relationship which we will be using very often there. Let's take an example here. Now, suppose you have a microwave radiation having a frequency of about 12 gigahertz. Suppose I want to calculate the wavelength of the radiation. How do I go about it? I will make use of the formula I just mentioned here, because we know that nu is equal to c by lambda. I can rearrange this and say that lambda to be equal to c by nu. C is my velocity of light or the velocity of radiation, and nu happens to be the frequency. The value of c is 3 into 10 to the power 8 meter per second, and frequency is given to me as 1.2 into 10 to the power 10 hertz, because 1 giga is 10 to the power 9. 12 into 10 to the power 9 can be written as 1.2 into 10 to the power 10 hertz or per second or second inverse. On solving, what we get is, we get the wavelength to be equal to 2.5 into 10 to the power minus 2 meters. So, very simple application of the straightforward formula there. Okay, let us move ahead and see yet another characteristic of EM radiation, that is your wave number. Wave number is given as nu prime. Now, this basically, as the name suggests, wave number, it is a number of waves or wavelengths per unit distance. Look at this picture here. Now, suppose I have taken a given distance here, say point A to point B here, a certain distance is there. If I look at these two waves here, I find that there are more of red waves in this particular distance than the blue ones there. So, the wave number of red is more as compared to that of the blue here. So, we see that the red wave has got more wavelengths in the given distance. So, we say that the wave number of this red wave here is more as compared to that of the blue wave here. Okay. Now, this wave number actually, as I just said, is denoted by nu bar. Nu is a symbol for frequency. So, if we take bar on that, that becomes our wave number, and actually it is reciprocal to the wavelength expressed in terms of meters. That is how do we visualize wave number. That means, you see what is the wavelength in meter, take the inverse of that, that becomes my wave number here. And the unit happens to be obviously meter inverse, because it is a inverse, it is a reverse of the meter there. So, it is a meter inverse. Typically, though SI unit happens to be meter inverse, but we normally use centimeter inverse as the unit, because the waves we come across belong to this domain here. And this wave number and wavelength are related as the following expression there, nu bar to be equal to 1 by lambda, that shows that is the inverse of the wavelength here. Another parameter is the energy. The energy of EM radiation basically is proportional to the frequency, that means E is equal to h nu is equal to h c by lambda is equal to h c nu bar. This is a very important relationship which we have to keep referring to very often there. So, we have to be clear about it. What we see from here is, that is, the energy is proportional directly to the frequency, inversely to the wavelength, and again directly to the wave number. This is very important here, and this proportionality constant h happens to be the Planck's constant, having a value of 6.626 in terms of minus 34 joule second, and c as before is the velocity of light, that happens to be 3 into 10 to the power 8 meter per second. And as I just mentioned, because of this proportionalities here, we can say shorter the wavelength, greater is the energy, because there is a inverse relationship there, because if this is smaller, energy will be more. And secondly, higher the frequency, if the frequency happens to be more, the energy will be more. That means, energy is directly proportional to the frequency there. So, this expression we will be using very often. Now, let us take another example again based on this particular relationship. So, suppose I have got a radiation, this blue light actually has a wavelength of about 490 nanometers. If I want to compute the energy of 1 photon of blue light, how do I go about it? So, essentially we know that E is equal to h nu or is equal to h c by lambda, we have just learnt about it. So, we have been given the value of lambda here, c is known to us, h is known to us. What we do is, we take h here, c we know of, lambda is given to us, we just make substitution and solve it. We find that this comes out to be 4.06 in terms of minus 19 joules there. So, very straightforward, but these are the important conversions which we will be doing very often in case of spectroscopy. Now, let us move on further and talk about what is called as electromagnetic spectrum, because we are talking about EM radiation, but there is a wide variety of EM radiations available to us depending on whether we talk in terms of frequencies or wave numbers or wavelengths. So, each one of them can be used to kind of talk about the spread of different types of EM radiations what we have here. The spread here is, that is, we can talk in terms of say increasing frequency in this direction or increasing wavelengths like this. So, what you have is of very low wavelength happens to be the gamma rays, then it becomes X-rays, UV, and then we got small visible range here, infrared, microwave, and so on and so forth. So, on this extreme we got long radio waves, on this extreme we got gamma rays here, and if we talk in terms of frequency, that is how they vary here. And what is important is that the visible part, the visible spectrum as we call it as, is a very tiny part of this whole EM spectrum range what we have with us, because we will be talking more about visible spectrum when we talk about UV visible spectroscopy. That is why this is important to know that all these colors we come across, they belong to very tiny part of the EM spectrum there. Okay, let us move further, because what we have done so far is we defined spectroscopy to be the interaction of radiation and matter. So, we have recalled what is radiation. Now, let us move on to see what is a molecule, because we know that we must have done some kind of a understanding of the molecular nature, and we know that the molecular energy levels are quantized there. And what we have is, in the case of a molecule, there are different types of quantizations possible there, that is the electronic energies are quantized, the vibration energies are quantized, and the rotation energies are quantized. So, there are three kinds of quantized energies we have in case of molecules. In case of atoms, things are very straightforward. You have a nucleus and there are different electronic energy levels there. Atoms is a simple case, but in case of molecules, we have got wide variety of energies which are quantized there. And second important thing which you have to take note of is here is, that is, electronic energies are far apart from each other. I mean this, because this is just a schematic representation, these values are very large. That means from this is my first level here, the ground level, this is my first excited state here, this will be enormous amount of energy there. As compared to that, these blue lines here or the green ones here, they represent the vibrational quantization energy levels for the ground state here and for the excited state over there. And this red bunch of lines here, they are the rotational levels which are quantized per say for this particular vibration energy level, they are the quantized rotation energy levels there. So, we have got three kinds of quantizations possible in case of a molecule. And when you talk about a spectroscopies, we will be talking about some kind of transition amongst these energy levels there. Okay. So, the important point is that we have got molecular energies which are quantized. We have got radiation, we have seen what they are, the characteristics of that. We also know the molecules now. Then when the two interact, what can happen there? When the radiation and matter interact, there are three possibilities. The first possibility is there is an absorption there. That means the molecule happens to be in one of the lower energy levels there, and it absorbs energy and goes to higher energy level. That is one possibility. That means energy is coming from the EM radiation there. Second possibility is, that is the molecule to begin with is in excited state, it emits radiation or gives out energy and comes down to lower energy level. And third possibility is some kind of a scattering coming into picture, because that is not in our domain, but I am just mentioning it for sake of it here. Now, let us understand, because we are going to talk primarily absorption spectrum. So, let us understand what is absorption here. Absorption basically refers to absorption of a suitable photon. That means a photon basically refers to one quantum of light or the EM radiation there or the energy here. So, this causes excitation from a lower energy level, say E1, to higher energy level E2. Let us understand this. Suppose there are two energy levels here, say level 1 and level 2, and say let me just take them to be say electronic energy levels there. Suppose let us say this is an electron here which is in the lower energy level here, and what happens is when the photon comes, it strikes the electron and this electron goes to higher energy level. That is the meaning of absorption. That means radiation is coming, falling on the system, and the system absorbs energy and goes to higher energy level. That is the meaning of absorption here. And these energy levels in principle could be electronic, vibrational, rotational, or even some other type. but for just the concept remains the same, that is there is an absorption from a given level to higher energy level there. And our interest primarily will be into the electronic and vibration transitions there. Electronic transitions will come into picture when we talk about a UV visible spectroscopy, and vibration transitions will be involved when we talk about the IR spectroscopy. So, in this particular course we are going to talk about two spectroscopies. So, our interest basically lies in these two kind of transitions there, and that is how do we represent them there. That means, we have got IR transitions, means we are going from one vibration energy level to another vibration energy level, and there will be some kind of a rotational energies coming there. We will talk about it when we come to the spectroscopies there. And UV and visible primarily will be, we have transition from one say electronic state here to another electronic state here. So, these are high energy transitions there. Vibration transition will be of lower energy over there. We will come to that when we talk in details about each spectroscopy there. Okay. Let us move a little further and see what is a spectrum. Spectrum basically is an outcome of this kind of interaction, and that basically is represented in terms of a graphical representation of the characteristic wavelengths. That means, suppose I am having a species which I want to study, and radiation is coming. When the radiation falls on it, whether it is absorbed or not, if yes, to what extent. So, all that is represented in terms of a graphical picture over there, and this is what is my spectrum looks like. This is one kind of a spectrum I can come across. For IR spectrum, there will be different kind of things there, and for other spectroscopies, we will have different kind of spectra. But the basic premise remains the same, that this is a graphical representation of the wavelengths or the frequencies or the wave numbers on typically on x axis, and on y axis we will have some kind of a parameter which tells you what the intensity of it. It could be absorption intensity, emission intensity, or something else over there. So, that is basically the kind of spectrum we will be coming across. And since we have got different types of interactions possible there, accordingly there are different types of spectrum. You can have absorption spectrum, you can have an emission spectrum, you can have even Raman spectrum. Raman spectrum is a kind of a scattering kind of spectrum there. So, there are wide varieties of spectra possible over there. Our interest primarily lies into absorption spectrum. So, let us see what is absorption spectrum. Absorption spectrum basically is a plot of the extent of absorption of radiation as a function of the wavelength, frequency, or the wave number. That means, my x axis here I am showing as wavelength, it could be wave number or it could be frequency or whatever, and on y axis will be the extent of absorption of that. We will explain that when we talk in detail about UV spectroscopy. But what is important is that if you look at the spectrum here, we find that there are two kind of broad bands over there. So, this is, since it is my wavelength on this x axis here, so this represents some kind of a lambda max. Lambda is the symbol for my wavelength there. So, this is first maxima here, this is my second maxima here. So, we will talk more about it later on. Let us see what are the characteristics of a spectrum. There are two things which you have to take note of. One is the position. Position basically, because we just shown you the spectrum, there are two peaks there. So, what is this position there? That position will be determined by the difference in the energies of the levels which are involved in the transition. That means, if I have an interaction there, the molecule is in certain level, from which level to which level is the transition taking place, that energy is going to determine the position of the signal there. And second is the intensity. That means, what is, because we have seen the spectrum here, we saw that one band was larger one, other was smaller there. So, this is more intense than this one. Why so? We will talk about it at a later stage. And the third is the width. We find that the two spectra, the spectra I showed you, the two bands had got different widths, that is spread of the wavelengths on the x axis, they form the width of the spectrum there. So, they are the three characteristics of our spectrum there. Position basically is determined by the difference I just mentioned here, and that is how we can rationalize that. We find that, now suppose I have got, this is my starting energy level from where the transition can take place, and suppose I have a transition from say this level to this level, or from the same level to yet another level there. So, you find that this transition involves more energy. So, it will be at a lower wavelength there, and since this transition A is of low energy, it will be at high wavelength there, because we know that the energy and the wavelength are inversely related there. So, that is the meaning of position there. As regards the intensity, intensity basically is little more involved thing. This basically depends on three things. One is the transition probability, second happens to be the population of the level from which the transition is taking place, and thirdly the concentration of the material which is interacting with the radiation there. This actually is little involved. We will take it up in the next session when we talk about the basics of UV visible spectroscopy there. Similarly, the third kind of characteristic of my spectrum, that is a width, also will be taken up in the next session only. Okay. Now, let us sum up what we have done today. What we have done today is we started by defining spectroscopy as the interaction of EM radiation and matter. So, since it pertains to interaction of radiation and matter, so we took up EM radiation, we described what is EM radiation, and then we explained different characteristics of EM radiation and also the interrelationships between them. That means, we talked about different characteristics like wavelength, wave number, frequency, etc., and then how are these things interrelated to each other. Having done that, we moved on to defining what is EM spectrum. That means, we talked about EM spectrum to be a spread of different kind of EM radiations possible with us, and then we also defined kind of described different regions of EM spectrum, and then thereafter we recalled the quantized nature of molecules, and in this context we recall that the molecular energies are quantized, and in case of molecules, besides electronic energy being quantized, the rotational and vibrational motion also are quantized. And we did talk about a kind of energy level, schematic energy level diagram, wherein we showed electronic energy levels, and then we found that each electronic energy level has got different vibration energy levels, and within one vibration, each of the vibration energy level has got the corresponding rotation energy levels there. So, there are three levels of quantization we have. Rotation quantization is of very small energies, vibration energies are higher, and the electron energies are still higher than that. And thereafter, we talked about the possible types of interaction between radiation and matter, absorption, emission and scattering and things like that. And then we came down to what is the meaning of a spectrum, how does a spectrum look like, and what are its characteristics there. And thereafter, we briefly touched upon explaining that how do we account for the position of a signal in a spectrum there, and as regards the intensity and the width, we have tried to defer it to the next session there, which we will be taking up very soon.